I've actually been asked a few times by different people about my coil design on my ZVS circuit. And so I wanted to make this video just to help people to show them what I have learned about making coils for these little induction heater systems, specifically in the application of heating cartridge brass, rather than something more designed for a forge or something like that. So the methods I'm going to be talking about and the design I'm going to be going for is something kind of specific to thin wall brass tubing and heating it up for annealing. Now, you can see this mess in front of me. I have learned by trial and error. I've learned a lot about this process. I've tried a lot of different things. Let me save you some time and money, because as you see on the table in front of you, I have tried a few things, and I've learned some stuff that doesn't work very well, and I've come across some things that do work fairly well. And so I'm going to, again, just go through the design of a coil and how you can figure out how big to make it, how many turns you need to make it, things like that, what materials you probably want to use, and some basics of design principles and some things to think about. So to start off, the coil that you design for induction heating is going to be driven by what is it that you're heating. And so, here I have a little piece of 223 brass, right? This dictates the type of coil that you need to make. What type of material are you heating, and what shape is the material you're heating? So cartridge brass is essentially thin wall brass tubing, and it's round. And so whenever you make an induction coil, you make it basically to mimic what it is you're heating. And so the reason why all of these designs are round is because they fit around the piece. And so that's the first element of design, is that you're going to be making a coil. Now, if you were heating something flat, like in an induction cooktop, they actually make pancake coils because they want a flat surface, because they are heating a flat surface. And if you look up industrial induction heating systems, you get all different kinds of coil shapes and designs based on what it is that they're trying to heat. And something like this, which is one of my bad attempts at making coil, would actually maybe be better suited for an internal heating of a pipe, where you could fit this thing down in it and it would heat a pipe around this thing. So they do make the induction heating work coils in various shapes. There's all kinds of stuff out there on that, for industrial heating purposes, but we're going to stick to coils because we are heating something round. So that's the shape that we need to make, is a round coil. Now, the second thing is, how big does the work coil need to be? And so I've got a few here that I've messed with. This was one of the ones that came with one of the little ZVS systems that I bought. And it's a 1/4 inch copper tubing, and this is just too big, frankly. If you look, it's just way bigger than the workpiece. And so this is not good for what we need to do. So typically the principles that dictate the size of the coil are the size of the workpiece. And the principles you need to think about is inductive coupling. How well does this coil transfer the magnetic flux to the workpiece? And the basic principles are, you want your coil to fit as closely as possible to the thing that you're trying to heat. The closer you can get the coil, the more energy will be transferred quicker, basically get denser flux on the workpiece. So typically what you want to think about is, what is the biggest, largest brass that you're going to heat? What's the maximum diameter? And then that's going to dictate the inner diameter of the coil that you need to make. You want it to be just a little bigger than your brass. Again, the biggest brass that you plan on heating. Large magnum brass, you're going to be looking at somewhere 14 to 15 millimeters max diameter for the brass to fit through the coil. So usually, I'm shooting for somewhere around 18 to 20 millimeters as an internal diameter for the work coil. So that's one element. The other element is we aren't trying to heat the entire piece of brass. So whenever I mentioned that, this was a bad design, the reason is it's got a lot of wasted coil. We really only want to heat the shoulder area. So in a perfect world, our coil would only be maybe this tall. Now, the reality is the material that we're working with is too large to really make that possible. But you do want your coil to not waste a bunch of magnetic flux. You don't want it to be too tall. You want your coil to fit the depth of the workpiece that you actually need to heat. And so that means you actually can't just wind, a ton of coil. And so that's why I've actually gone to using double layer designs, because that allows you to do more turns in the same height. And the reason that's important is that the number of turns along with the diameter of your coil set the inductive properties of the coil, and that interacts with your ZVS system, the capacitors of that system, to determine the frequency. And the frequency of your system also influences the coupling with the workpiece. So when it comes to determining what type of coil, again, the shape's going to be round. The size, the inner diameter, is going to be driven by what you're heating. The height is going to be dictated by what you're heating. But then you also have to fit in a correct number of turns based on the size of the coil so that you get the right inductance value. And so I'm going to talk through how to set that up as well. Right. So far we've got the size. We know some things that, the size is going to be determined by the workpiece. We know that we need to take into consideration the frequency that we want to operate at. And then the last thing is, what type of power handling do you need this coil to accommodate? So this has some insulation on it, but the copper itself, this is a 3/16 or about 5 millimeter outside diameter coil, whereas this little sucker right here is 1/8. And so it's much smaller diameter tubing. So this stuff, this little copper tubing, is easy to work with, but I've found that it doesn't actually work very well once you take into consideration the power that you're probably going to want to run. It's just too small. Now, it's not too small for the power itself. The problem is whenever you're doing inductive heating, heat gets generated. And so there's two sources of heat that are going to pop up in this system. One type is resistive. So by running the oscillating current through this coil, the coil itself will heat up. Now, if you design everything properly, you can use anything that is conductive to make your coil. You could make your coil out of just cable or wire, and it would work as far as the inductive properties. The problem is, if the thing heats up, this has poor dissipation because it's just going to radiate on the outside. Now, again, like I said, if you do everything properly, your coil actually won't heat up too much. You could actually make this thing out of like Litz wire, and it would heat up very, very little if it were properly designed. So actually, the resistive heating of the coil itself isn't that big of a problem. You really don't need to use tubing, except for the workpiece gets really hot, right? We're going to be heating this sucker up to 1,000 degrees or more, and that thing is going to radiate heat into the coil. And so it's actually not the heating of the coil that you really have to worry about. It's the coil being heated by the workpiece. And so you've got to deal with that heat. And so the easiest way to do that is to use tubing and get that thing to focus, and then water cool your coil, right? And so that handles the heat problem really well. But whenever you use 1/8 inch tubing, you don't get much water flow. And so that's the problem with using this really small tubing, is I found that it did not water cool very well. I didn't get much flow. And if you don't get good water flow, you just boil the water inside this coil. Now, the small diameter tubing also has lower current carrying capacity, so it does heat up more than the larger tubing that I've been using. So its actual coil heat was higher, and it was less able to get that into the water because less water could flow through this thing. You would need pretty high pressure to really get good water flow through this small diameter tubing. So bigger diameter tubing flows a lot better. You can handle a lot more power. You can get a lot more water flow. But then you can go too far and use something like 1/4-inch tubing. And the problem with this is that it's really hard to get really tight bends out of this big tubing, and you get really big coil height for the number of turns you need. And so what I found is the best size so far for me has been this 3/16 copper tubing, because it allows for tight enough bends, it allows for a short enough coil height, but it's still big enough to allow good water flow. And so that's what I'm going to use to make my coils until I find something better. Is going to be this 5mm or 3/16 diameter copper tubing, because it's going to handle what I need it to handle, allow for the water cooling, and be able to fit into the design envelope that I need to make this coil. Now, the next section to come up is, all right, so we've got our material. We know some parameters about the size that we need. So how do you know how many turns to make this thing, right? That's the next step. And for that, we're going to head to the computer, and I'm going to do some calculations and show you how you can figure out how many turns you need in your coil. Okay, so one of the things that we're going to have to understand whenever we go to design our work coil is how the inductance of the work coil sets the frequency of our circuit, and here's the math behind that. And the thing that you really need to pay attention to is down here in the bottom right, this little equation for the resonant frequency of our circuit. And so as you can see in this, the formula for the frequency in our circuit is going to be 1 divided by 2 times pi times the square root of the product of the inductance and capacitance in our ZVS, where the inductance L is the inductance of our work coil, and the C is going to be the capacitance of the capacitor bank in our circuit. And so those are the things that we need to know. What's the capacitance? And then we'll need to know what frequency we want, and then that will determine what inductance we want our coil to have. So here's a spreadsheet that I've got set up to do this calculation, and you can see in this frequency box the equation 1 divided by 2 times pi times the square root of the capacitance times the inductance, which I'm pulling from column D, and then I'm just reformatting those numbers here to show you the values in microfarads and microhenries. And to get in our frequency range, we have to know what capacitance that our circuit is going to have. Now, this depends on how many capacitors you're using in your capacitor bank and what size they are. If you're using like the induction cooker capacitors that you can find on like eBay and Amazon, usually you're going to get 0.22 or 0.33 microfarad caps. And if you're using 10 of them, you're going to get like 2.2 to 3.3 microfarads. And so in my circuit, I actually have 3.3 microfarads. And if I use a 1 microhenry inductance coil, I get a resonant frequency of about 87 kilohertz. So if I reduce that to about 0.8, I get up closer to 100. If you go down to like 0.6, you're up to 113. 0.5 is going to be, getting to where kind of the top end of our range. So really, if you've watched my previous video, I am using a coil that's more around 1 microhenry, apparently, because I am getting somewhere. It could be even as high as like 1.5, right? Because my circuit resonates somewhere between 70 to 85 kilohertz. But, honestly, that works fine. You don't have to be super precise in this. And kind of, the end result of this analysis with 3.3 microfarads, anywhere from half a microhenry up to 1.5 actually works. That's kind of fine. Now, if you go down to 2.2, that means you could go up to maybe 2 microhenries and as low as, it looks like 0.7, and you'd probably still be fine. So you actually have a pretty wide range of inductance values that works. And that's good. That gives us some room for error in making this coil, because in the real world, our materials and execution isn't going to be perfect. So, that puts us in the ballpark. We're looking for probably anywhere from, 0.8-ish microhenries, down to 1/2, up to 1.5, in that range for most circuits is going to work. So the next step is to use this to calculate, well, how many turns do we need to make our winding on our coil? So for that, I'm going to use a website. And so here it's from electronbunker.ca. It's a multi-layer induction calculator. And so in order to use this, we have to tell it the parameters that we think might work, and then it's going to calculate the inductance. And so I can give you some tips on where to start out. So in this calculator, you can do it in inches or you can do it in millimeters. I'm going to do it in millimeters. It allows you to specify multi-layer coils, and then it will calculate the inductance. And so the parameters that you need, first I would start off with the diameter of your coil form. That's going to be the interior of your coil. Now, so if you're doing cartridges, you need to make this big enough so that it will fit through. And if you're doing any sort of automation, you want to make sure that you have a big enough diameter here for the cartridge to fit through easily without getting snagged. So let's say that we want to enter a diameter of, somewhere 16 to 18 millimeters. You also want to point out if you're going to use an insulating sleeve, you can enter that here with the conductor size and the wire diameter, including the insulation. Now I'm going to leave the insulation off. I'm going to plan this without any insulating sleeve. And I'm going to be using a 3/16 of an inch diameter tube. So if we take 3/16 of an inch and then convert that to millimeters, it's 4.7625 millimeters. Now you will find whenever you get 3/16 inch copper tubing that sometimes you will actually get 5 millimeter tubing. So you might want to go ahead and measure your tubing if you want to be more precise. I don't care that much. I'm just going to use this value for this demo because the reality is you're going to get some variation in the actual end result. Anyway, the operating frequency is just because the inductance of the coil changes at different frequencies. We're going to leave it alone because we want to know what the true inductance is. And then again, the frequency gets set by resonance in the circuit. So go ahead and leave that out. The coil shape is circular, so we don't need to leave anything in this box. The axial pitch. So if you scroll down, it actually gives you an outline of what these things are, right? And so the pitch axial, that's going to be the distance from center to center of our coil. And so that's typically going to be one diameter of your conductor plus the insulation here, right? So it's usually this if they're stacked tight. Now, if you leave any gap, that's going to increase this. So basically what this axial pitch is the total diameter of the conductor plus insulation plus any gap. Now, if I plan this to have very, very little gap and I'm using a 4.76 millimeter conductor, I'm going to do like 5 millimeters, and that's going to leave hardly any gap in between those. You do need some gap or else you'll get conduction between the coils, and you don't want that. So I'm going to have 5 millimeters pitch. Now here's where you got to kind of play around with it. I'm going to do a dual layer coil, and let's start off with 4 turns, and let's just see where this gets us. Calculate this. It tells us the radial pitch. This is another thing. I'm going to go ahead and put that 5 too. The radial pitch, by the way, if I scroll down, is the distance this way. And again, I want to leave a little bit of gap, so I'm going to do that 5 millimeters. Calculate that, and it gives me the corrected inductance of 1.08 microhenries. Back here, if I do 1.08 microhenries, that tells me I would be at 84,000 or 84 kilohertz with a 3.3 capacitance with 2.2. I'd be where I'd want. So this would work with the 2.2 microfarad capacitor bank. if I'm running 3.3, it's going to be a little too high. So I want to bring this down lower. All right. So I need to reduce the number of turns. So I could go to a single layer with 8 turns, but this actually ends up in this calculator. You can see it also tells you the total coil length. And this is one thing to pay attention to. 39.7 millimeters. And let's just call that, 38 millimeters divided by 25.4. It's an inch and a half. That's actually really long. Really, I would probably like to be something like an inch or an inch and a quarter, maybe max. An inch is 25 millimeters long, so I really don't want to have my coil length that far. So that's why I'm going with a dual layer coil, and 4 turns was too much. What happens if I go to 3 turns? Calculate. My coil length is going to be really short, and my inductance is going to be kind of more correct. Now, the last thing I would point out is you actually can't do 6 turns. If you do 6 turns, the ends of your coil will be doing opposite directions because you'll be going a full 360 degrees. You actually need to add an extra half turn. So that will be a quarter of a turn per layer. We hit calculate, and that gives us 0.7859, 0.7859, and that's going to put us in the range we want to be. So it looks like what we need to do is form an 18 millimeter coil form, and then do 3 1/4 turns per layer, which ends up being a grand total of 6 1/2 turns, and that will end up with our leads both facing the same direction on our coil, and it's going to give us a resonance in our circuit in the range that we want. All right, so that's the plan on the coil that we're going to make. Again, we're going to do a 6 1/2 turn total, and that should give us kind of what we want. So let's see how that turns out. Okay, so kind of with the base coil set, the next video we're going to get into actually making this coil, and then we'll measure it and we'll see kind of how it turned out.